Okay, so let's start today's lecture. Okay, so last time we have been starting to talk about like the solution. Okay, so like the solution theory. Okay, so solution theory of systems of differential equations. Okay, so systems of differential equations. Okay, so the key point here is to kind of rewrite the system of differential equation. So let's say the first, okay, so system of first order differential equations. Okay, so let's say first order, okay, so differential equations. So the key point is that if you have a system first order differential equation, it must look like x1 dot is equal to p11 of t of x1 plus dot 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 plus p1n of t of xn plus the q1 of t. Let me say g1 of t. Okay, so let me say g1 of t, and then it's kind of x2 dot is equal to p21 of t of x2 plus dot 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 plus p2n of t of xn plus g2 of t. So you continue doing that until you get xn dot is pn1 of t of xn plus dot 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 plus pnn of t of, okay, so sorry, so here is x1, right? So it's still x1. Okay, so of xn plus the gn of t. Okay, so that's the kind of the way how you write down a system of first order equations. Now, if you let like x of t is equal to x1 of t in terms of vector matrix notations, you're going to set the p of t to be the matrix which consists of p11 of t until p1n of t, and then here is the pn1 of t until pnn of t. Okay, so and then you're going to set the g of t. Okay, so to be equal to the coefficient g1 of t until you reach gn of t. Okay, so that's what you would like to have. Then you're going to see, okay, so then you're going to see that this equation can be simply written as x dot of t, okay, so is equal to, okay, so p, okay, so the coefficient matrix multiplied by x of t plus the vector g of t, right? So that's the kind of what we call it the vector matrix notation. Okay, so vector matrix notation, right? So that's the equation in a vector matrix notation. Okay, so and this is what we call it the non-homogeneous system. Okay, so this is what we call it the non-homogeneous system. Now the corresponding homogeneous system is going to kind of remove the g of t. You're going to just write everything as a homogeneous system. Okay, so this is the so-called homogeneous system, right? So this is the so-called homogeneous system. So you have this non-homogeneous and homogeneous systems, and similarly as what we did before, we have to kind of explore the solution theory for the homogeneous and non-homogeneous systems. So you should start from the homogeneous system and then go to non-homogeneous system. So the rationale is the same thing, same rationale as we had before, right? So same rationale as we had before. So that's kind of the thing that we would like to start from the homogeneous systems of equations. Okay, so now for the homogeneous system, we have the so-called principle of superposition, which is a very simple theorem. It just says that if x1 is a solution, right? So let's say x1 dot of t is equal to p of t of x1, right? So x1 of t, and then x2 is another solution. So x2 dot of t is equal to p of t multiplied by x2 of t. Then you're going to see that d by dt of c1x1, right? So c1x1 of t, okay, so c1x1 of t plus c2x2 of t is equal to p of t multiplied by c1x1 of t plus c2x2 of t. right? So that's kind of it's kind of a very simple linear relation, which simply tells you that so x of t is equal to c1x, right? So x1 of t, right? So plus c2 x2 of t is a solution, right? So this is called superposition principle, right? So this is the so-called superposition principle. So that's kind of a very simple principle, which simply tells you that if you have like one solution, okay, so then their linear, I mean, if you have two solutions, then their linear combination is going to give you a solution. Is a good family, right? So that's kind of very simple relation, which is kind of analogous to what you had in the for the higher order equations. So that means for the general solution, okay, so the general solution x of t of this homogeneous system should be defined as a combination. Okay, so I from 1 to n, ci xi of t, where these xi's are the so-called fundamental solutions. Okay, so you're going to have like an analogous fundamental solution theory where in order to really have the fundamental solutions, you're going to study the so-called Wronskian, right? So the Wronskian, we have been talking about Wronskians for our original higher order equations. Okay, so let's say a small review. Okay, so a small review of what we had before is that if you had kind of have like higher order equation, okay, so let me say, okay, so let me say a n of t y n's derivative, right? So plus dot 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 plus a0, okay, so a1, okay, so let's say plus a1 of t, okay, so of the y prime plus a0 of t of y is equal to 0, right? So that's the higher order homogeneous equation. Then you're going to say that the general solution is a c1y1 plus dot dot dot, right? So c1y1 of t plus dot 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 until you reach, okay, so plus dot 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 plus cn yn of t, right? So that's kind of what we learned before, where this y1 and yn are called fundamental solutions in the sense that the Wronskian wy1 up to yn, which is the determinant y1 up to yn, and then y1 prime up to yn prime, dot dot dot, until you reach yn minus 1's derivative, until yn minus 1's derivative. This guy has to be non-zero because you're going to have such a notion of the Wronskian. Is that good, February? Okay, so that's what you had, what we had before. Now, correspondingly, in our theory here, we're going to have like the system of first order equation. So x dot of t is equal to p of t of x of t. This is a homogeneous first order equation where this matrix is n by n. Okay, so the x is equal to x1 dot 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 xn, right? So and the p of t is equal to p11. Okay, so until you reach p1n and pn1. Okay, so until you reach pn. So these are n by n matrices. Now in that case, you have similar solution. The x of t is equal to c1 x1. Okay, so I'm going to call it fundamental solution. So the x1 of t plus dot 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 plus cn of the xn of t. So that's kind of a very much analogous to what you had before, where the x1, xn are so-called fundamental solution. So that you're going to kind of form the Wronskian of this matrix vectors x1 up to xn, right? So what is the Wronskian of a vector? Well, the Wronskian of a vector was introduced before. It's just a determinant of these vectors treated as column vectors in a row. Okay, so that what I'm saying is that this is nothing but the determinant of this x1. Okay, so until you reach the xn. So what does this mean? Well, the determinant has to work for a square matrix. In order to work for a square matrix, you're going to kind of treat x1 as x1, the first component, right? So the x1 as the nth component. So this is the first vector. And then you're going to kind of align all these column vectors in a row. So xn, the first component, until you reach xn, the nth component. So this is actually a square matrix. You just want this square matrix to have a determinant that is non-zero. Is that good for everybody? Okay, so this is a very important, okay, so this is a very important analogy between what we have before and what we have now. Okay, so that's kind of the very important analogy between what we had before and what we have now. So remember, the Wronskian of all these vector functions is that you put all these vectors as column vectors in a row. Okay, so column vectors in a row, and then you're going to say that you take the determinant of this square matrix as a resulting square matrix, then you're going to reach this determinant. So what actually happened here, let me re-emphasize, what actually happened here is that you're going to treat this x1, okay, so you're going to treat x1 as x11 as x1n, right? So this is a column vector in the row. So until you reach xn is equal to xn of 1 dot 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 xn of n, right? So there's a column vectors in a row, and then you're going to kind of calculate the determinant of x1 up to xn. Well, this determinant is going to work for a square matrix because each one is each of these vectors is a column vector. You put them in a row. This is actually the determinant of the matrix x11 up to xn1. Okay, so until you reach x1n up to xnn, and you want this determinant to be non-zero. So that's what you would like to have for this determinant theory. Is that good for everybody? Okay, so this is going to be kind of very important for your understanding of the Wronskian for vector functions. Okay, so that's all for this. Okay, so for this, which I kind of wrote it here. Okay, so where you set each column vector as a column vector, and you put them in a row, you calculate the determinant. So we are reaching a theorem that's analogous to what we had before, which says that if you have vector functions x1 up to xn and they're linearly independent, which means that these vectors form a Wronskian that's non-zero, right? So they are linearly independent. Then the Wronskian is non-zero. Okay, so conversely, if the Wronskian is non-zero, then they are linearly independent. So this is like analogous to what we had before. Okay, so this is like analogous to what we had before. So this is kind of very important thing to construct like fundamental solutions for vector matrix equations that is homogeneous, right? So this is a homogeneous equation, like what you have here, the homogeneous equation. You're going to form a Wronskian is non-zero, then they're going to form fundamental solution, and arbitrary solution is a linear combination of them. Okay, so that's kind of theory. So now let's look at an example. Okay, so this example is about the Wronskian calculation. It says that can you calculate the Wronskian of the vector form of these two functions? Okay, so of these two functions. Okay, so I want to calculate the Wronskian of these two functions. Okay, so what we are going to do here. Okay, so what we are going to do here is to kind of compute, right? So is to kind of compute the Wronskian of these two functions. Okay, so just one moment. Okay, so I want to calculate Wronskian of these two functions, right? So of these two functions. So what we have to do? Well, you can see that they are column vectors in a row. So that means you just calculate the Wronskian of x1 of t of as well as x2 of t, right? So you treat column vectors in a row. So that's going to be the determinant of e power minus t minus 2 e power minus t and e power 3t and 2 times e power 3t. You treat column vectors in a row. And you calculate determinant, so that's going to be just a cross, right? So do a cross and subtraction. So that's 2 times e power 2t minus of minus 2 e times e power 2t. So that's going to be 4 times e power 2t. This is going to be non-zero, right? So the e exponential function is never equal to 0, which means that these two column vectors, right? So these two solutions are linearly independent. So that means x1 of t and x2 of t, right? So x1 of t and x2 of t are linearly independent. Okay, so that means they are linearly independent. So that's kind of a very simple exercise. Okay, so that's kind of very simple exercise just to show you what happens there. Okay, so now we can summarize our analogous comparison, saying that if you have vector functions x1 up to xn, they're linearly independent solutions of the homogeneous system of equations, then the general solution can be represented as a linear combination of this fundamental solution. So what I'm saying here is that this picture, this comparison here. Okay, so that means if you have fundamental solutions, which means that this x1 up to xn are the solutions of the homogeneous equation, then you do a linear combination of these solutions. I mean, as long as the determinant is non-zero, the Wronski is non-zero, they are fundamental solutions, and you have a unique representation of your general solution to the homogeneous system just by a linear combination of these fundamental solutions. Is that good, family? Okay, so this whole theory is completely analogous to what you had before for higher order equations. Okay, so it's just a natural extension of what you had before. Okay, so that's the content of this theorem. Okay, so which says that if the vector functions x1 up to xn are linearly independent solutions of x prime is equal to ptx, then as long as the determinant of the Wronskian, right? So the Wronskian determinant is non-zero, then the general solution is just a c1x1 plus dot 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 plus cnxn represented as a linear combination of the solutions x1 up to xn. And how do you determine the CIs? Well, you determine the CIs by solving a linear system of equations. Okay, so let me summarize what we had before. Okay, so now let me summarize this whole procedure. Okay, so let's say let me summarize this whole procedure of what we did so far. Okay, so let me summarize this procedure. Okay, so to summarize this procedure, it means that first of all, you're going to kind of write. Okay, so I have already done this step, so I'm going to kind of skip it a little bit. You're going to write this homogeneous first order equations as vector matrix notation. So this was done at the very beginning of today's lecture. As long as you have such a system of equation, you can introduce these notations and you kind of abbreviate everything into this vector matrix form. As long as you have the vector matrix form, you're going to find these solutions x1 of t until you reach xn of t, forming fundamental solutions. Okay, so let's say forming fundamental solutions. Okay, so they are forming fundamental solutions. By fundamental solutions, it means that the Wronskian of x1 up to xn. Okay, so the Wronskian up of x1 of t up to xn of t has to be non-zero, right? So that the Wronskian is non-zero, but the Wronskian, as we just talked about before, it is equal to determinant of x1 of t until you reach xn of t. Right? So you put column vectors in a row, you calculate the determinant, that's the Wronskian. As long as you have this, it means that the general solution, okay, so the general solution is going to be a linear combination of all these fundamental solutions, so that x of t is c1 x1 of t plus dot 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 plus cn xn of t. So that's going to be a general solution, which is a linear combination of these fundamental solutions. Now, how do you find particular solutions? Well, remember, this is a first order equation, so that initial condition, okay, so when you take initial conditions, initial conditions have not been talked about before, but let's look at here, okay, so that's if you want to put initial conditions for this equation, then you're going to say that initial condition, okay, so let's say initial condition, okay, so the initial condition here is going to say that y of 0 is equal to y0 and dot 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 until you reach yn minus 1 of 0, right? So n minus 1 of 0 is equal to y0 n minus 1. So you have to, because this is an nth order equation, you have to put n initial conditions starting from the 0's derivative until the n minus 1's derivative. Is that good for everybody? Okay, so what happens to the initial conditions here? Well, the initial conditions here is you're going to just say that the x of 0 is equal to some vector x0. That's only one initial condition compared to many of them. Why is that the case? Because this is only a first order equation. You just have to specify the vector at the very initial point. So this is a vector equation, meaning that each component is the same. Okay, so what I'm saying here is that the initial condition, okay, so the initial condition should take the form x, okay, so x of 0 is equal to x0 vector, which simply means that x, okay, so which simply means that the solution x1 of 0 dot 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 until you reach xn of 0, they're going to be equal to x1 0 until you reach xn of 0. So this is a vector equation, meaning that these two vectors are going to be the same. Is that good, family? Okay, so once you have these initial conditions, you're going to pass from general solution to particular solution, right? So you're going to pass from the general solution to particular solution. Now, how do you pass from general solution to particular solution? You have to set the initial conditions. So that means x of 0 is equal to c1 x1 of 0 plus dot 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 plus cn xn of 0, and you're going to set them to be x of 0. Okay, somebody is going to ask, well, here the unknown variables are c1 up to cn, and you want to solve for n unknown variables. It looks like you have only one equation. Is that good, family? But it doesn't quite matter. Okay, so it doesn't quite matter because I can conclude with the following. Okay, so let's say if you have the initial condition. Okay, so if you have the initial condition. Okay, so if you have the initial condition, it's going to say that the x of 0 is c1 x1 of 0 plus dot 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 plus cn xn of 0 is equal to x of 0, right? So there exists. So we can say we can find. Okay, so we can find unique. Okay, so unique c1 up to cn from the above equation. Okay, there are two ways to view this. Okay, so one way is to say that, okay, so let's say rationale. Okay, so there are two ways to view this. One way is to say that since the x1 of 0 until the xn of 0, okay, so xn of 0 are linearly independent. Right, so are linearly independent. Right, so these are linearly independent solutions because, right, so because the Wronskian of x1 of 0, okay, so they are linearly independent because the Wronskian x1 of 0, okay, so xn of 0 is equal to non-zero. The Wronskian is non-zero, they are linearly independent. In general, you are going to say that the Wronskian for any t is non-zero. In particular, at point 0, the Wronskian is 0, so linearly independent. But since last time, right? So since last lecture, we've been talking about linear independency, which means that, okay, so this which means that any linear combination summation I from 1 to n ci of xi of 0 is equal to 0 is going to imply that c1 is equal to, okay, so let's say is equal to cn is equal to 0. Is that good, for it, right? So that's kind of the what happened here. So then how do you find a unique c1 up to cn? Well, the situation is very simple because if you have, okay, so if you have summation 1 to n, okay, ci, okay, so let's say ci xi of 0 is equal to a fixed vector, okay, x0. Remember, here's a 0, here's a fixed vector. But if you have another solution, okay, so 1 to n ci theta of xi of 0 is also equal to x0. So if the solution c1 up to cn is not unique, then you probably have two such possible choices of the ci. Then you're going to see that summation I from 1 to n ci minus ci theta multiplied by the vectors xi of 0 is 0. So it comes to this linearly independent definition. But this linearly independent definition is replacing the coefficient ci by ci minus ci theta. So that actually is going to tell you that ci minus ci theta is equal to 0, which means the ci equal to ci theta for I from 1 to n, which means that you're going to have a unique solution. Is that good, for everybody? Okay, so that's one way to find the unique solutions. Okay, so to guarantee that you're going to have a unique solution for your particular solution. Is that good for everybody? Okay, so once you find the unique C1 up to Cn, you're going to get a particular solution, right? So you're going to get a particular solution, which is nothing but the x of t is equal to the summation I from 1 to n ci x, okay, so xi of t. Okay, so that's going to particular solution. So that's the one way to view this. Another way to view this is more practical. Okay, so to be more practical, you're going to say that I know that x1 of 0, this is a vector, so that we can say it's x11 right of 0 dot 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 x1n of 0, so that's a vector, and you're going to reach like xn of 0 is going to be x, okay, so xn1 of 0 dot 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 xnn of 0. These are going to be vectors, right? So I'm going to write these vectors explicitly as column vectors with given coefficients. And now I'm going to set this x0 to be equal to x01. Okay, so let's say x0n. Okay, so that's going to be the right-hand side. So then you're going to see that c1 x1, okay, so of 0 plus dot 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 plus cn xn of 0 is going to be equal to x0 is now the same thing as a system of linear equations, c1 x11 of 0, okay, so plus dot 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 plus cn x1n of 0 is going to be x01. And you continue doing that. So c1, okay, so that's going to have, you're going to have, okay, so you're going to have c1 x1n, okay, so of 0 plus dot 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 plus cn xn of 0 is equal to x0, and so that you're going to have this equation. Is that good, family? Now we're going to treat, when we treat these equations, we're going to treat the c1 up to cn as unknown variables. Okay, so we're going to treat c1 up to cn as unknown variables. So that being said, it's kind of probably better to write this equation into a system of, okay, so linear equations that are of the following form. Okay, so they're going to be of the following form, that it's going to say that's x11 of 0 multiplied by c1. So let's say multiply by c1 plus dot 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 plus x1n of 0 multiplied by cn is equal to x01. So and same thing for all these equations. So that's xn1 of 0 multiplied by c1 plus dot 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 plus xnn of 0 multiplied by cn is equal to x0n. Is that good, family? Okay, so that actually being said, you have a system of linear equations. How do you guarantee a unique solution? Well, in order to guarantee a unique solution, you just need the determinant of the coefficient matrix to be non-zero. Is that good, family? Right? So that means you just need the determinant of the coefficient matrix to be non-zero, right? So determinant of the coefficient matrix, which is the determinant of this coefficient matrix, x11 of 0 dot 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 xn1 of 0 dot dot dot, right? So x1n of 0 dot 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 xnn of 0, and this determinant has to be non-zero in order to guarantee that you're going to have a unique solution for the system with unknown variables c1 up to cn. But this determinant is nothing but the Wronskian, right? So because the Wronskian of x1 of 0, right? So dot 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 up to xn of 0 is just the determinant is non-zero. We are guaranteed that these are fundamental solutions, which means the Wronskian is already non-zero. So that actually being said, it means that there is going to be a unique choice of C1 up to Cn. And you set this C1 up to Cn there, you're going to find this particular solution. So these are kind of two rationales to view this passing from the general solution to the particular solution. And the second rationale is kind of more practical because it kind of tells you a way to find a C1 up to Cn. Namely, you just want to kind of review this x1 up to xn as a coefficient vectors, and then you're going to kind of solve this linear system. You're going to find the solution C1 up to Cn. Is that good, everybody? Okay, so that's the rationale of how you work with this homogeneous system of linear equations. And you first, so let me repeat, you first find the fundamental solutions by saying that these are solutions to the original equation and the Wronski is non-zero. And then the general solution is formed as a linear combination of these fundamental solutions. And how do you find linear combinations? Well, you find the linear combinations by setting a linear system of equations. You solve for the C1 up to Cn. Is that good, family? Okay, so that's kind of a general procedure which we summarize about solving these differential equations. Is that good, family? Okay, so that's kind of the thing. Okay, so now there is a kind of a side remark. How do you get a set of fundamental solutions, right? So we're going to kind of tell you how to get a set of fundamental solutions, starting from maybe second part of today's lecture. But there is a theorem saying that if you set the E1 to be the vector with the first component 1 or the other components 0, and you set the E2 to be the vector with second component 1 or the other components 0, etc. And then these fundamental solutions are going to be the solutions, particular solutions of the system of linear equations with the corresponding initial conditions to be E1 up to En. That's going to give you a set of fundamental solutions. Okay, so this is only a side remark. Okay, so this is only a side remark just for you to let you know what about these fundamental solutions. Is that good, family? Okay, so now by the end of today's lecture, I would like to talk about, okay, so I would like to talk about an example. Here it says that can you find a constant matrix A such that the vector functions are the solutions of x prime equal to A log x. Okay, so that what happened here is that first of all, you have to kind of tell me what's the size of A. Is that good, family? Okay, so of course we are talking about this equation x dot, right? So is equal to A of x, right? So and therefore the size of A should match the size of x, right? So and what are the solutions given you? Well, the first solution is like e power minus t minus 2e power minus t. Second solution is e power 3t and 2 times e power 3t, right? So that's kind of a two, the dimension 2 vectors. So the A must be like A, B, C, D. Okay, so it must look like A, B, C, D. It must be 2 by 2 matrices. Is that good, family? Okay, so now what are these fundamental solutions? Well, these solutions here are going to be given by, okay, so just one moment. Okay, so right, so the solutions here are going to be given by e power minus t, right? So e power minus t. Okay, so the solutions here are going to be given by, okay, so by these two solutions. Okay, so that's these are the solutions that we considered in this scenario. Is that good, family? Okay, so once you have these two solutions, it means that it means that the x1 is a solution, so that x1, okay, so x1 dot of t is equal to A of x1 of t. You're going to have this equation. Now, what is x1 dot? Well, x1 dot of t, you're going to see this is minus e power minus t. You just take derivative, and then it's 2 times e power minus t is equal to the matrix A is A, B, C, D is going to be multiplied by e power minus t and minus 2 times e power minus t. Is that good, favorite? Okay, so this is going to give you a kind of a very nice relation. It tells you that A times e power minus t, okay, so minus 2 times B times e power minus t is minus e power minus t. And then we're going to say A e power minus t. Okay, so C e power minus t, right? So C e power minus t and minus 2 times D times e power minus t is equal to 2 times e power minus t. Is a good fabric? Okay, so that means the e power minus t is a factor that can be cancelled. So you get such a nice relation that a minus the 2b is equal to minus 1 and c minus the 2d is equal to 2. So these are kind of two relations between the a, b, c, d. Okay, so these are kind of two relations between the a, b, c, d. Now you can do the same rationale. Okay, so you can do the same rationale for the x2 of t, right? So for the x2 of t is e power 3t and 2e power 3t, so that you're going to see that x2 of t, okay, so if you take a derivative, it's also equal to a times the x2 of t. So then you're going to take those derivatives e power 3t is 3 times e power 3t, and then this 2e power 3t is 6 times e power 3t. We take this derivative, that's going to be equal to a, b, c, d multiplied by the vectors e power 3t. Okay, so e power 3t and 2e power 3t. Is that good for everybody? So this is going to give you the relation 3 times e power 3t is a e power 3t plus 2b e power 3t, and then it's 6 times e power 3t is c e power 3t plus d times 2d e power 3t. Okay, so you're going to have this. Now, as long as you have this, it means that you get another set of relation which tells you that a plus the 2b. So you can cancel this e power 3t's. Okay, so a plus 2b is equal to 3, and c plus 2d is equal to 6. Is that good for everybody? Okay, so you combine these two relations. Okay, so you combine this two system of set of equations that you obtained, right? So you combine these two set of equations that you have obtained, right? So just one moment. Okay, so we get this set of relation. Okay, so we get this set of relation, and we get this set of relation. Is a good family, right? So you get these two set of relations from which you should be able to solve the ABCD. Is a good family, right? So how do we solve this ABCD? Well, you can have a plus, so that means a is equal to, you add these two equations divided by 2, so that's a equal to 1, and then b is equal to 1 again. Is a good family, and for these two equations, the c is equal to 4, and then the d is equal to 1. Is that good family? Right? So now you can find ABCD. Once you find ABCD, you get the matrix A is equal to ABCD, right? So that's what we had before. So that's 1, 1, okay, 4, and 1. So that's the matrix A. Is that good family? Okay, so this is kind of getting you familiar with the system of 2 by 2 linear equations. Okay, so here is as an exercise, as exercises, I've been listing kind of 2 different exercises that help you to get familiar with this chapter. Okay, so with this material, is that you're going to turn a higher order equation into a system of equations and express the equation in vector matrix notation. And similar here, if you have a system of higher order equations, you're going to kind of transform this equation into first order differential equation, system of differential equation, and then write it in matrix vector notation. Okay, so I hope these 2 exercises will help you. I mean, you can practice by yourself, and it's kind of I hope you will it will help you understand the material a little bit better. Okay, so this is about like the general theory of systems of homogeneous high order system of differential, first order differential equations. So now starting from now, okay, so starting from now, we're going to talk about a very particular situation for the system of homogeneous equations that you're going to be tested. Okay, so these are for sure. Okay, so I can say for sure to be tested in your upcoming exams. Okay, so what are we talking about? The setting here. Okay, so we're going to talk about the following setting. Okay, so the following setting, the equation has to have the form x dot of t is equal to a of x of t with a certain initial condition x0 is equal to x0, where the A is 2 by 2 matrix. Okay, so this is going to be very important. A is going to be A, B, C, D. This is 2 by 2 matrices. Is that good for everybody? Okay, so these are 2 by 2 matrices. And the solution you would like to find is also 2 by 2. So that's x1 of t of x2 of t. Is that good for everybody? Okay, so, and this is going to be kind of a very typical type of problems that you're going to see on your upcoming exams. We're going to call them 2 by 2 constant coefficient homogeneous equations. Okay, so let's say 2 by 2. Okay, so 2 by 2 constant coefficient. Okay, so constant coefficient, right? So homogeneous systems. Okay, so the 2 by 2 constant coefficient homogeneous systems are going to be kind of a typical type of example that you will see in a lot of your upcoming lectures and exams. So that's what you're going to be interested here is like the homogeneous linear systems of constant coefficients. Okay, so that means you just want to kind of interested in x prime is ax, where A is a 2 by 2 matrix. Okay, now how are we going to solve it? Okay, how are we going to solve it? Well, you can see that if this equation, so in order to get an idea how to solve this equation, you have to kind of analogy. Okay, so analogously, if your equation is y prime of t is equal to ay of t, then what you're going to try? Well, you're going to try like y of t is equal to e power of at with constants. But here, since you have replaced y by x, you have to kind of raise the small a to capital A, which is a vector. So that's kind of e power at is something that is hard to understand, right? So because you're raising a matrix to an exponential. Is that good, family? So that's hard to understand. So it looks like this is not a good way to treat this problem. But also remember that if you have like, let's say, for example, a constant, because we're talking about constant coefficient. So let's say if it is a constant coefficient, higher order equation. Okay, so let's say a1 of t, y prime of t plus a0 of t, y of t. If it is a constant coefficient equation, then you're going to try the same, right? So we're going to try the so-called fundamental solutions, where y of t is e power r of t. R is the solution of the so-called characteristic equation, right? So a1 of, okay, so there's no t. Okay, so this is a constant coefficient equation. Okay, so a1 of r plus a0 is equal to 0. This is what we call the characteristic equation. Is that good for me? Okay, so that's what we call the characteristic equation. Basically, you want to try a function of an exponential with an unknown exponent. So you can do the same thing here. Okay, so you can do the same thing for this x dot of t is equal to e power, okay, sorry. So x dot of t is equal to a x of t. This is like a system of, system of constant coefficient equations. Then you're going to say that your x of t is equal to e power, okay, so rt, right? So e power rt, but the x of t has to be a vector, right? So because the x of t here is a vector, so here this is only a scalar, right? So it's only a scalar, but here you're going to have a vector. So in order to reach a vector, I'm going to say, okay, so I'm going to say that there is a kind of an unknown vector. Okay, so an unknown vector. So let me call this vector x. Okay, so let me call this vector x. X is a fixed vector. Is that good for everybody? Okay, so x is a fixed vector. Is that good for everybody? Okay, so once you have this form of this equation, as you obtained, how you obtained the characteristic equation, well, if you kind of set this solution, yt is e power rt, you set it back into this original equation, then it is going to give you the characteristics. Is that good for everybody? Right? So that's kind of, remember, we're going to have the fact that k's derivative is r to the power of k and then y. Is that good for everybody? Right? So you're making use of this relation. Now, same thing as here, so that you can see that x dot of t, because x is a constant vector, so that this is going to be r times e power rt of the constant vector x. And this one has to be equal to a times e power of rt multiplied by x. Is that good for everybody? Okay, so therefore, because the e power rt is never going to be 0, you can kind of cancel both sides. So that's going to give you a minus ri of this x, right? So it is going to be equal to 0. Is that good for everybody? Okay, so, and what does this tell you? Well, according to the linear algebra that we studied in the previous lecture, it means that a of x is equal to r of x. So that means you have two things to talk about. First thing is that r is an eigenvalue. Okay, so r is an eigenvalue of a. And second thing is to say that x is an eigenvector. Okay, so eigenvector of a. Is that good for everybody? Okay, so this is going to be very important. It means that if you're solving this constant coefficient 2x2 linear equations, the whole problem is reduced to eigenvalues and eigenvectors. Is that good for everybody? Okay, so basically it means that you're looking for a solution that looks like this, right? So you're looking for a solution that looks like this, where the R is going to be the eigenvalue of A and the X is going to be the eigenvector of A. So that you just need to find the eigenvalues and eigenvectors. Okay, so that's kind of what you have here. So here I replaced, I used the cosine to represent the X, right? So I was using this X as a vector, but in the lecture notes, I was using cosine. Okay, so the reason I changed the cosine into X for the lecture is because the cosine is a Greek letter, and not everybody, including me, from this class is from Greece. Okay, so with some people in previous semesters of teaching, they're not they do not recognize what cosine is because they don't know Greek language. Okay, so let's say make it life simpler. We're not going to use Greek letters. We're just going to say it's X. Okay, but anyway, after this derivation, you get this relation A psi is R psi, which is an eigenvalue and eigenvector problem, which means R is the eigenvalue and psi is the eigenvector. So there are actually here, the situation is that we're working with constant coefficient 2x2 matrices. Okay, so if the equation is a 2x2 matrix, then 2x2 matrices always admit 2 eigenvalues as well as 2 eigenvectors. Is that good, family? Right? So this is like what we have kind of discussed in the previous lecture when we talk about linear algebra. So there are 2 eigenvalues and there are 2 eigenvectors. Okay, if you have 2 eigenvalues and 2 eigenvectors, then the situation is going to be the following. Okay, so let's say A. Okay, so it is equal to A, B, C, D is a 2x2 2x2 matrix. Then you solve the eigenvalue eigenvector equation. So Ax is equal to R of X, right? So eigenvalue eigenvector equation. You're going to get the first eigenvalue is R1. The first eigenvector is X1. Is that good, family? Okay, so and then you're going to get second eigenvector value R2 and a second eigenvector X2. Is that good, family? Okay, so then the general solution. Okay, so the general solution to the homogeneous problem is going to say that X of t is C1. Okay, C1. Then what you're going to do? Well, as before, because this is an exponential multiplied by the constant vector, so that's e power R1t of X1 plus C2 e power R2t of X2. Is that good, family? Okay, so some people are going to be confused because previously you were just saying that I will just combine xi of t, ci xi. So why is not c1 x1 plus c2 x2? Here I have to kind of warn you. Okay, so I have to warn you that this x1 and x2 are not solutions, right? So if you look at this problem, the solution in general form is x of t is e power rt multiplied by the constant vector x. Is that good for everybody? So that means if you find R1, then you're going to see x1 of t, the actual solution that we were talking about here, x1 of t is actually should be equal to e power R1 of t multiplied by the first vector x1. And same thing here, x2, R2 is giving you x2 of t is kind of e power R2 of t multiplied by the vector x2. Is a good family, right? So as long as you have this, you can see that this is nothing but C1 x1 of t plus C2 x2 of t. It just agrees with our previous theorem. It's just you have to realize this x1 and x2 are constant vectors. They are eigenvectors of the eigenvalue eigenvector equation ax equal to rx. Is that good, family? Okay, so in our lecture notes, this x1 and x2 are replaced by cosines, which are kind of easier to recognize. Basically, I'm saying that this is, okay, so basically what I'm saying is that this is going to be your x1 of t, and then this one is going to be your x2 of t. They're going to be the fundamental solutions. Is that good, family? Okay, so this is going to what we're going to have for this situation. Okay, so but we have to kind of warn you for a second thing. Okay, so we have to kind of warn you for a second thing before we close this lecture is that this only happens when R1 and R2 are both real numbers and R1 is not equal to R2. The reason here is kind of you can check about the Wronskian. Okay, so you can check about the Wronskian of these two solutions, and you're going to see that this is the case when you're going to produce a fundamental solution. Okay, so maybe I'll stop the lecture here, and I will continue talking about these systems of second order equations, second system of first order equation of 2 by 2 from next lecture. Okay, so that's what I want to say for today's lecture, and let's continue in the next lecture. Okay, so that's all we say for this lecture, and let's stop here.